the Chinese coastline, engineers are building massive tunnel sections the size of 10-story buildings, entirely on dry land, inside custom-made factories. Then, in a single 12-hour window, they float these enormous concrete structures out to sea, sink them precisely into place on the ocean floor, and connect them together underwater with a level of accuracy that would make most engineers anywhere else in the world nervous just watching. This isn't science fiction. This is happening right now, off the coast of Guangdong province, where China is building one of the most ambitious undersea crossings ever attempted. The project is called the Shenzhen-Zhongshan Link, and it connects two of the most important economic zones in the entire country. But the real story isn't just about a bridge or a tunnel. It's about a construction method so radical that when Chinese engineers first proposed it, foreign experts openly doubted it could be done. Sinking a tunnel section is one thing. Sinking dozens of them, each one weighing as much as an aircraft carrier, and getting them to align underwater with millimeter precision is something else entirely. However, China didn't just attempt this once. They've now done it repeatedly, refining the process each time, turning what used to be one of the riskiest operations in civil engineering into something that almost looks routine. So how exactly do you build a tunnel on land and then sink it into the ocean without it collapsing, flooding, or drifting off course? And why is China betting so heavily on a construction method that most countries consider too dangerous to attempt at this scale? Let's get into how it actually works. To understand why this method exists at all, you need to picture the Pearl River Delta. This is one of the most congested, economically vital regions on the planet. Shenzhen sits on one side, a city that didn't even exist as a major metropolis 50 years ago and is now a global tech hub worth more than most entire countries. Zhongshan and the western side of the delta sit on the other side of a wide, busy waterway. For decades, people and goods traveling between these two areas had to take a massive detour, driving all the way around the bay or relying on slow ferries. The distance as the crow flies is short, but the actual driving distance, before this project, could take over 2 hours because of the shape of the coastline. That's 2 hours of trucks stuck in traffic, factories waiting on parts, and workers wasting time on commutes that should take 20 minutes. In an economy that moves as fast as China's manufacturing corridor, that kind of delay costs real money every single day. So the obvious answer was to build a bridge. And in fact, part of this project is a bridge. But here's the problem. The waterway isn't just busy with cars, it's one of the busiest shipping lanes in the world, with massive container ships moving in and out of the ports at Guangzhou and Shenzhen around the clock. A bridge tall enough to let those ships pass underneath would have to be so incredibly high that it would interfere with flight paths from the nearby Shenzhen Baoan International Airport. This is the kind of problem that stops most infrastructure projects dead in their tracks. You can't build the bridge tall enough because of the airport. You can't build it low enough because of the ships. Something has to give. The solution the engineers landed on was to combine a bridge with a tunnel. Build a bridge across the parts of the waterway where ships don't need extreme clearance. And then, where the shipping lanes are busiest, drop down into an underwater tunnel that ships can pass directly over. It's an elegant idea on paper. In practice, it meant building one of the longest and deepest undersea tunnels in the world, in an area with strong currents, soft seabed conditions, and constant ship traffic that couldn't be paused for years while construction happened. And that's where the real challenge began. Because building a tunnel under an active shipping channel isn't like digging a tunnel through a mountain. You can't just bore through solid rock. You're working underwater, in mud, in currents, next to some of the busiest ports on the planet. The first method anyone considers for underwater tunnels is called drilling and boring, where a giant machine chews through the earth beneath the seabed, similar to how tunnels are dug under cities. But for a project this wide, this shallow beneath the waterline, and this close to shifting silt and soft mud, boring wasn't a realistic option. The seabed here is made up of soft clay and silt that has been building up for thousands of years, layer after layer of loose sediment that a boring machine would struggle to move through safely. Therefore, engineers turn to a method that has existed in various forms since the early 20th century, but had never been attempted at this scale or under these specific conditions. It's called the immersed tube method, and it works almost exactly like it sounds. Instead of digging through the earth, you build individual tunnel sections somewhere else entirely, then transport them to the site and sink them into a trench that's been prepared on the ocean floor. Think about it like assembling a drainage pipe out of massive concrete segments. Except each segment is longer than a football field, wider than a highway, and has to be lowered into place underwater with almost no room for error. This is where the story gets genuinely wild, because building these tunnel segments isn't something you can just do on a random patch of land. China constructed an entire dedicated factory, essentially a purpose-built shipyard for tunnel sections, on an artificial island near the construction site. This facility exists purely to manufacture these gigantic concrete tubes one after another, almost like a factory line, except each individual unit is a structure heavier than most buildings. Each tunnel segment, known as an element, is roughly 160 meters long. To put that into perspective, that's longer than 1.5 football fields laid end to end. Each one is also incredibly wide enough to fit 6 lanes of traffic inside, 3 lanes going each direction, plus additional space for emergency corridors and utility systems. And each one weighs an almost unbelievable amount, somewhere in the range of 74,000 tons when fully constructed. That's heavier than most naval aircraft carriers. Building something this massive on land already sounds difficult, but the real challenge is that these elements can't just be built like a regular building. They have to be built as watertight, structurally reinforced shells capable of surviving underwater pressure, resisting corrosion from seawater over a 100-year lifespan, and withstanding the kind of stress that comes from having millions of tons of water pressing down on them from above. The construction process for each element starts with an enormous reinforced concrete base, built inside what's essentially a massive dry dock. Steel reinforcement bars, thick enough that a single one is difficult for 2 workers to lift together, get woven into an intricate lattice structure inside the mold. This steel skeleton is what allows the tunnel to survive decades of underwater pressure, seismic activity, and the natural settling that happens when something this heavy sits on the seabed. Once the steel framework is in place, concrete gets poured in massive, carefully controlled stages. Pouring too fast, or letting the concrete cure unevenly, can create microscopic cracks that would compromise the tunnel's watertight seal decades later. So the pouring process happens slowly, layer by layer, with constant monitoring of temperature and curing conditions, sometimes over a period of weeks, for a single element. After the base and walls are formed, workers install an inner waterproofing membrane, a specialized coating designed to prevent even a single drop of seawater from penetrating into the tunnel's interior. This membrane has to be applied with obsessive precision, because a tunnel section with even a small leak becomes catastrophic once you're dealing with the pressure of dozens of meters of ocean water sitting above it. But here's the detail that surprises most people when they learn about this process. These tunnel elements aren't hollow shells waiting to be filled with equipment later. They're built almost complete before they ever touch the water. Road surfaces, drainage systems, ventilation shafts, even some of the electrical conduit. All of it gets installed while the element is still sitting in the dry dock on land. Because once this thing is floating in open water, headed toward its final position, there's no going back to add forgotten details. Once construction of an individual element is finished, and it has been tested extensively for structural integrity and watertightness, the next challenge begins. And this is where things get almost cinematic in scale. The dry dock where these elements are built is designed with a controlled flooding system. Once an element is fully constructed, engineers slowly flood the dry dock basin, allowing water to gradually fill the chamber. As the water rises, This 74,000-ton concrete structure, something that should, by all logic, sink like a rock, actually begins to float. The reason this works comes down to basic physics that becomes genuinely impressive at this scale. Each tunnel element is sealed completely airtight before flooding begins, with temporary bulkhead walls installed at both ends. This means the massive concrete structure is essentially a giant sealed box, similar in principle to how a submarine or a ship's hull works. Because the overall structure displaces more water than its actual weight, once submerged partially, it becomes buoyant enough to float on the surface, even though it's made almost entirely of solid, reinforced concrete. Watching one of these elements float for the first time is apparently one of the most nerve-wracking moments for the engineering teams involved. Everyone knows the physics should work. The calculations have been checked and rechecked. But when you're watching a structure heavier than a naval warship slowly lift off the floor of a dry dock and begin floating on open water, there's an instinctive part of your brain that expects disaster. But it doesn't sink. It floats, stable and controlled, ready for the next phase of its extraordinary journey. Once an element is floating, it gets carefully towed out of the dry dock and into open water using a fleet of specialized tugboats. These aren't ordinary tugboats. They're purpose-built vessels equipped with advanced positioning systems, capable of moving something this massive at incredibly slow, controlled speeds, sometimes as slow as 1 or 2 kilometers per hour, to avoid any sudden movements that could damage the structure or create dangerous waves. The journey from the factory to the final tunnel location can take several hours, depending on weather conditions, tidal patterns, and shipping traffic in the area. And this is where the operation becomes an enormous coordination challenge. Because remember, this entire waterway is one of the busiest shipping lanes on the planet. Before a single tunnel element ever leaves the factory, authorities have to coordinate a temporary shutdown of shipping traffic in the immediate area. Container ships, some of the largest vessels in the world, have to be rerouted or delayed for hours, while this massive concrete structure makes its slow journey to its final resting place. Weather forecasts have to be nearly perfect, because rough seas or strong currents could make positioning this 74,000-ton object extremely dangerous or even impossible. This is why the entire operation, from towing the element out of the factory to finally sinking it into position on the seabed, typically has to happen within a single 12-hour window. Once the process begins, there's no pausing halfway through. The tidal conditions, the weather windows, and the shipping traffic coordination all have to align perfectly. And once that window opens, the team has to move fast and precisely to get the entire operation done before conditions change. So how do you actually sink something this massive with enough precision to connect it seamlessly to the tunnel section that was placed before it? This is genuinely one of the most technically impressive parts of the entire process. Before any tunnel element even leaves the factory, divers and underwater survey teams have already spent weeks, sometimes months, preparing a trench on the seabed exactly where this element needs to sit. This trench has to be excavated to an incredibly precise depth and shape, because the tunnel elements need to sit at a specific angle and elevation to eventually connect together into one continuous, level tunnel. Preparing this underwater trench involves specialized dredging equipment that removes soft seabed material and creates a stable foundation layer, often made of compacted gravel that the tunnel element will eventually rest upon. This foundation has to be checked and rechecked using sonar mapping and underwater surveying equipment, because even a few centimeters of unevenness could cause serious problems once the massive concrete element is lowered into place. Once the trench is ready and the tunnel element has been towed to the exact location above where it needs to sink, engineers begin what's called the immersion process. Remember those sealed bulkhead walls that allowed the element to float? Now, in a carefully controlled sequence, water gets pumped into internal ballast tanks built into the structure. As these tanks fill with water, the element gradually loses buoyancy and begins to sink in a slow, deliberate, and carefully monitored descent. This isn't something that happens by feel or estimation. GPS positioning systems, Underwater sonar tracking and real-time data feeds allow the engineering team to monitor the element's position down to the centimeter as it descends toward the seabed. Divers stationed underwater provide additional visual confirmation, watching as this colossal structure slowly approaches its final resting place. The moment of connection is where all of this precision truly matters. Each tunnel element needs to connect to the one placed before it, with a watertight seal capable of withstanding decades of ocean pressure. To achieve this, each element has a specialized rubber gasket system installed around its connecting face, similar in concept to a rubber seal on a refrigerator door, except this seal has to work under intense water pressure and remain functional for 100 years. As the element descends and gets close to its final position, hydraulic systems and guidance mechanisms help align it precisely with the previous section. Once contact is made between the two massive concrete faces, engineers pump water out from between the two connecting elements, creating a pressure differential. This pressure difference essentially uses the weight of the ocean itself to push the two elements together, compressing that rubber gasket seal and creating a watertight connection between two structures that together weigh well over 100,000 tons. Once this connection is confirmed and tested, the temporary bulkhead walls that allowed the element to float are eventually removed, since the seal against the neighboring element and the surrounding water pressure now keeps everything watertight and stable. From this point forward, that individual element is no longer a standalone floating structure. It's a permanent part of a continuous underwater tunnel. But building one of these connections successfully is one thing. This project required dozens of these connections, each one just as critical as the last, repeated over and over across an underwater tunnel that stretches for kilometers beneath the busiest shipping channel in the region. And here's something that makes this project even more remarkable when you consider the broader context. This wasn't China's first attempt at immersed tube tunneling. Just a few years earlier, engineers completed the Hong Kong-Zhuhai-Macau Bridge project, which also included a massive undersea tunnel using similar technology. That project was, at the time, considered one of the most ambitious infrastructure undertakings in modern history, and it gave Chinese engineering teams invaluable real-world experience with the immense complexities of this construction method. However, the Shenzhen-Zhongshan link pushed the technology even further. This tunnel needed to be built in water conditions with significantly stronger currents, softer seabed material, and even higher standards for structural durability, given the sheer volume of daily traffic the tunnel is designed to handle. Engineers had to refine nearly every aspect of the process, from how tunnel elements were manufactured to how underwater trenches were prepared, in order to meet these new challenges. One of the most significant advancements came in the form of an improved sealing and connection system that allows for even more precise alignment between tunnel sections while also improving the long-term durability of each connection point. Chinese engineers developed proprietary sealing compounds and reinforced gasket designs specifically to handle the unique water pressure and current conditions found at this particular site. Another major innovation involved embedding sensors directly into each tunnel element during construction. These sensors allow engineers to continuously monitor stress levels, temperature fluctuations, and even minor shifts in positioning over time, long after the tunnel has been completed and open to traffic. Instead of waiting for a problem to become visible or dangerous, engineers can detect microscopic changes in the tunnel's structural behavior years in advance, allowing for proactive maintenance rather than reactive repairs. This kind of long-term monitoring capability might not sound as flashy as sinking a 74,000-ton concrete tube into the ocean, but in terms of engineering significance, it may end up being just as important. A tunnel like this is expected to remain in service for at least 100 years. Building in the ability to detect problems decades before they become critical could end up saving enormous amounts of money and preventing potential disasters far into the future. Of course, a project this massive and this technically demanding didn't come without serious challenges along the way. The Pearl River Delta's soft seabed conditions created persistent complications throughout the construction process. Engineers had to continuously adjust their trench excavation techniques to account for shifting sediment layers that didn't always behave as predicted by initial geological surveys. Weather posed another constant threat. Typhoons are a regular occurrence in this region of China, and even a moderately sized storm could create dangerous conditions for towing and sinking tunnel elements. Construction schedules had to remain flexible, sometimes delaying planned immersion operations by days or even weeks while teams waited for a safe weather window to open up. There was also the sheer logistical challenge of coordinating with one of the busiest ports in the world. Every single tunnel element immersion required careful coordination with maritime authorities to reroute or delay shipping traffic, a process that had to happen dozens of times over the course of the project, without causing significant economic disruption to the shipping industry that relies on this waterway daily. And then there's the human element of this story, something that often gets overlooked when discussing massive infrastructure projects like this. Thousands of engineers, construction workers, divers, and specialized technicians dedicated years of their lives to this project. Divers who worked underwater to guide these massive elements into position were operating in challenging conditions with limited visibility, strong currents, and the psychological pressure of knowing that even small mistakes could have catastrophic consequences. Despite all of these challenges, the project moved forward, element by element, connection by connection, until the tunnel was finally completed. The tunnel now allows vehicles to cross what used to be a 2-hour detour in a fraction of that time, dramatically improving connectivity between two of China's most economically significant regions. So why does all of this matter beyond just being an impressive engineering achievement? The Shenzhen-Zhongshan link represents something bigger than just a bridge and tunnel connecting two cities. It represents a shift in how massive infrastructure projects can be approached and executed. Traditional construction methods, especially for undersea crossings, have historically required either extremely long construction timelines or compromises in design that limit a project's overall effectiveness. By perfecting the process of building tunnel elements on land and then transporting and sinking them with incredible precision, Chinese engineers have essentially created a repeatable, scalable model for undersea tunnel construction that other countries are now studying closely. This construction method also demonstrates something important about how China approaches infrastructure development more broadly. Rather than treating each major project as an isolated challenge, Chinese engineering teams consistently build upon lessons learned from previous projects. The knowledge gained from earlier immersed tube tunnels directly informed improvements made during this project, and it's likely that lessons learned here will influence future undersea tunnel projects, both within China and potentially around the world. There's also a broader economic and strategic dimension to consider. The Pearl River Delta region, which includes cities like Shenzhen, Guangzhou, Hong Kong, and Macau, represents one of the most economically significant urban clusters on the planet. Improving transportation connectivity within this region isn't just about convenience. It's about enabling faster movement of goods, people, and economic activity across an area that plays a critical role in global manufacturing, trade, and technology development. By reducing what used to be a 2-hour journey to a fraction of that time, this project effectively brings previously separated economic zones closer together, allowing for more efficient collaboration between industries, easier commuting for workers, and faster movement of goods between manufacturing centers and shipping ports. In an economy where time genuinely equals money at a massive scale, these kinds of infrastructure improvements can have ripple effects that extend far beyond the immediate area. It's also worth considering what this project represents in terms of engineering confidence and ambition. When immersed tube tunnel technology was first developed decades ago, projects using this method were relatively modest in scale compared to what's being built today. The willingness to attempt something at this scale, with tunnel elements this massive, in water conditions this challenging, reflects a level of engineering confidence that has been built up over years of incremental experience and technological refinement. And this raises an interesting question about what comes next. If Chinese engineering teams have now successfully demonstrated the ability to construct undersea tunnels of this scale and complexity, what does this mean for future infrastructure ambitions? There have already been discussions about even more ambitious undersea tunnel projects in other parts of the country, potentially connecting regions separated by even wider or more challenging bodies of water. Some engineers have even speculated about whether this kind of technology could eventually be adapted for extremely long-distance undersea tunnels, potentially connecting entire countries or continents separated by relatively shallow waters. Of course, it's worth acknowledging that this construction method, however impressive, isn't without its critics and concerns. Some engineers outside of China have raised questions about the long-term environmental impact of large-scale seabed dredging and trench preparation required for these projects. Disrupting seabed ecosystems, even temporarily, can have lasting effects on marine life in the surrounding area. Chinese engineering teams have implemented various environmental mitigation strategies throughout this project, but the long-term ecological impact remains a topic that requires ongoing study and monitoring. There are also questions about cost. Projects of this scale and technical complexity require enormous financial investment, and some critics argue that the resources dedicated to these mega infrastructure projects could potentially be better allocated toward other pressing needs. However, proponents argue that the long-term economic benefits generated by improved connectivity and reduced transportation times ultimately justify the massive upfront investment required. Regardless of where you land on these broader debates, it's difficult to deny the sheer engineering achievement represented by this project. The ability to construct tunnel elements this massive, transport them safely through some of the busiest shipping lanes in the world, and sink them into place with millimeter-level precision, all within carefully coordinated 12-hour windows, represents a genuinely impressive combination of engineering skill, logistical coordination, and technological innovation. As construction techniques continue to evolve, and as engineering teams around the world study the lessons learned from projects like this one, it's likely that immersed tube tunnel technology will continue to advance even further. Future projects may push these techniques into even more challenging environments, potentially opening up new possibilities for infrastructure development in coastal regions around the world that have historically been considered too difficult or too risky for undersea tunnel construction. The Shenzhen-Zhongshan link stands today as a powerful example of what becomes possible when decades of incremental engineering experience come together with massive ambition and careful, methodical execution. What used to require a 2-hour detour around a busy waterway now takes a fraction of that time, thanks to a construction method that involves building entire tunnel sections on land and then sinking them into the ocean with a level of precision that continues to push the boundaries of what modern engineering can accomplish. And as more countries look toward China's rapidly evolving infrastructure capabilities, it raises an important question about the future of global engineering competition. Will other nations attempt to replicate this kind of large-scale immersed tube tunnel technology? Or will China continue to lead the way in developing and refining these incredibly ambitious undersea construction methods? Only time will tell, but based on what's already been accomplished here, it's clear that the boundaries of what's considered possible in undersea infrastructure continue to expand every single year. If you found this breakdown of one of the most impressive engineering feats in the modern world interesting, consider subscribing for more deep dives into the massive infrastructure projects shaping our world today, projects that most people never even hear about, but that quietly reshape entire economies and regions. There's likely another video on your screen right now covering a similarly ambitious project, so if you're curious about what else engineers around the world are building right now, that video is a great place to go next.